Good day, Evan Snyman from Machlocal, Making a Difference. Today we're looking at functions and inverses, specifically the topic of exponents and logarithms. Okay, so this fancy word logarithm might be a bit of a shock to you. It comes from the Greek. Let's have a look at what it actually means. So if I gave you the equation 2 to the x equals 8, you would quite happily tell me that therefore x equaled 3. But if I told you that 2 to the x equaled 9, you might have the sense that therefore the answer must be a little bit more than 3, but you wouldn't know immediately what the answer would be. So you'd know that the answer was x is 3, but what? Okay? Because we know that 2 to the 4 equals 16, so therefore, because 9 lies in between 8 and 16, we know the answer must lie in between 3 and 4. You probably also have a good sense that the answer therefore must be 3,2, maybe 3,3, but we don't know exactly what that answer is going to be. Now, a logarithm is, again, we've been talking about inverses, so if we can say that my rule is throwing in this number leads me to say, cool, 2 to the power of it gives me 9. So we are now trying to undo this idea of an exponent. And this is where a log comes in. Okay. Now the shortened form of the word logarithm is simply to say a log. Okay. So we are saying therefore that from 9 I must be able to get back to this number. So what we now say is therefore x equals log base 2 of 9. Okay. So this is not magic. I'm not getting this phrasing from nowhere. Let's have a look at what we are saying. Okay, so I'm saying that if we can say 2 to the x equals 9, then we are able to say that the inverse of the statement is to say, therefore, that x equals log base 2 of 9. Now, I want to quickly emphasize something. What was the role of the 2 on the left-hand side here? Well, the 2 is below the exponent, and so we would call it the base. And I would like you to see that the 2 over here has the same role. Okay, so here on the left, it was base 2, and on the right here, it is still going to be base 2. Okay, and by coming across, that base of 2 has now become the base of the exponent. Now on your calculator, you have a button that looks as follows. Okay, it says log something of something. So I'm literally going to type that into my calculator right now and tell you what the answer is. Okay, so log base 2 of 9 is, and my calculator is saying to me it's 3,169925. Okay, so we now know that x equals, okay, we knew it was going to be a bit more than 3, and now we know specifically it's going to be 3,16299, sorry, lies, a little bit back, typo, reading it badly, 3,16, not 299, but 992. Okay, so again, the calculator will find out what the logarithm is, okay, and will undo this idea of a exponent. Okay, now in the same way, if a exponent and a log are the inverse of one another, then a log and an exponent are the inverse of one another. So if I gave you something along the lines of, cool, therefore log 2 of x equaled 4, okay, and I did not know how to solve that, well, then I would simply pull out the inverse. Well, what's the inverse of a log function? The inverse of a log function is an exponent. And an exponent requires a base and a power. So there's my base 2. So we would therefore know that x would be equal to 2 to the power of 4, which we know is 16. So that means I can solve fancy exponential equations, and I can solve logarithmic equations using the idea of the definition, which effectively talks about what is the inverse of its function. Okay, so a exponential function and a log function are inverses of one another. Now, why can I say that these things are inverses of one another? And why can I say that the inverse is also a function? Well, again, let's go back and look at some theory. Okay, so we knew that if I looked at an exponential function, so let's look at, for example, the exponential function of f of x, a silly setup, f of x equals, let's do something really, really simple, 2 to the x plus 1. Okay, so we know it's going to have an asymptote sitting over here at 1. And we know it's going to be an exponential function, so it's going to do something along the lines of that. And we know that because this is this is at 1. Okay, so let's put it in a different color just to make it a little bit clearer. So because we know this thing is at 1, and we know that this point here will be at 2, and let's pick another point here. Let's choose the point 3 and 9. Okay, we know that 2 cubed is 8 plus 1 is 9. So we know that this is a fair sketch of our drawing. Now, again, if we run horizontal and vertical line tests across here, we would see that it cuts the graph once. If you run horizontal line tests across this thing, until we got to the asymptote, it would cross once. So we know that this thing is a 1-to-1 function. Okay, which is really important because that means that if I run it backwards, okay, I'm also going to get a 1 as an output when I run it backwards, which means that the inverse relationship will also be a function. Okay, so let's have a look at what that would look like, and then let's talk about what it would be as a graph. Okay, so amongst the various things we said with an inverse function is, in terms of trying to find it, we would swap x and y around. And what we said is that if we looked at the graph, we would see it as being swapping x and y around. So let's have a look at what that would be for this particular function. Well, if we have a horizontal asymptote going through 1, and I swap that idea around, that means I will now have a vertical asymptote going through 1. Okay, and I'm swapping the idea of the x and the y around. So whereas I had a horizontal asymptote, now I have a vertical asymptote. The equation of that old horizontal asymptote was y equaled 1. The equation of this vertical asymptote is x equals 1. Okay. Now, if we don't know how to draw this function yet, and that's okay, it's the first time we're seeing it, we can see that, hold on, the green original function has got a y cut at 2, which means that the new function, the inverse function, must have an x cut at 2. Okay? And if the new function has got a value of 3 and 9, so if the original function has a value of 3 and 9, then the inverse function will have a value of 9 and 3. So here would be the value of my new function. Now hold on. How does a graph get from this point here at 2? Okay, so how does it get from this point here to 2 up to that point there and still have an asymptote? Well, that means it must be doing something along the lines of this. Okay, it's curving towards that. Okay, and it must be coming down here and approaching the asymptote. Okay, so it's asymptotic down here. Now, again, if you think about that, it makes sense. If it is if the original exponential function is asymptotic to the, approaches the asymptote towards negative infinity, well, that's going to be the same for the inverse function. It will approach the asymptote towards negative infinity. Okay, so here we have our picture. We can see that this is going to be a fair picture. Again, it should not surprise us that the line y equals x is the mirror between these. Okay, and again, here is our line y equals x, acting as the line of reflection between a graph and its inverse function. Okay, in this particular graph, these two graphs do not seem to intersect each other at any point in time, and so there's no real major concerns there. Okay, what about this blue graph's equation? Can we find the equation of f to the minus 1 of x? Well, we've been through this before. We can do our steps. Okay, 1, write it in y notation. So we're going to write y equals 2 to the x plus 1. Okay, we're going to do our swap of x and y. So x equals 2 to the y plus 1. And now we're going to work to get y by itself. So we first are going to take the minus the 1 across. And we're going to have x minus 1 equals 2 to the y. And now we're going to remove the base 2. And to remove the base 2 means we're going to take log base 2. So I've got log base 2 of x minus 1 equals y equals f minus 1 of x. Now, how does this fit in with other pieces of graphs that we know? Well, if we think about it, what does the minus 1 over here do to the function? Well, doesn't that minus 1 mean you move everything to the right 1 unit? Or as you're looking at it, to the right 1 unit? Okay, so therefore, what we've got here is consistent with other pieces of graphing that we've done. Okay, so again, everything we can see in the graph, okay, that an exponential function and a logarithmic function, okay, are reflections in the line y equals x, and that they are inverse functions of one another, can be seen also in the algebra. Okay, so whereas we'd move the green graph up 1 by adding 1 after the fact, in the case of the inverse function, we've moved the graph 1 to the right, which is the positive movement. Okay, so we moved it 1 to the right, but instead of doing it after the fact, we're doing it before the fact, because now the sequence is different. Okay, so we can now be asked to sketch logarithmic graphs. Okay, we can now be asked to sketch logarithmic graphs, and again, let's just think this thing through. So when I had a exponential graph, okay, we knew that an exponential graph did one of two things. Okay, it either took off, okay, and that would have been our asymptote. So if this is y equals k to the x, we know that this is the graph if k is greater than 1. In the same way, we would have a graph that many teachers, many people refer to as an exponential function that is landing. Okay, and we'd have a graph that is doing that. Okay, and this is what happens when k is between 1 and 0. Now hold on, let's think things through. It is because there's a restriction on the variable. Okay. Okay. And there's a restriction that says, sorry, the handwriting here is getting horrible. I'll try to write a bit slower. That says, therefore, k must be greater than 0. K may not be negative. K may not be negative. In fact, it may not be 0 either. Okay. So your base may never be negative or 0. It must be positive. The output, interestingly, you might notice here is always a y value that is greater than 0. Okay, so we know this is a limit on your range. Okay, so your range is always, in this case, positive. Now, I know that changes as you shift the graph up and down, and that's acceptable. Okay, but your y value is also stuck here. So let's go look at, therefore, what would happen if we looked at a log function. Okay, let's again just quickly get a log. Let's get this nice little graph here. Okay, cool, cool. So let's have a look here at what's going to happen to a log function. Okay, so if we look at the log function, okay, the log function will do the following. Okay, it will effectively try to take off, but it will flatten out as it takes off. Okay? And so this is the function of log base something y equals log. We'll talk about that now. Okay, k of x. My fault. Let's just quickly undo log k of x. Okay, this is where k is greater than 1. Okay, and it will come down to land in the same concept, same idea. It will come down and try to land if k is less than 1, greater than 0. Okay, so again, you can see there's a restriction. The restriction here is that k has got to be greater than 0. It's the same restriction. This restriction should not surprise you. It is the same restriction as we had here. But again, there is a second restriction. What we might notice here is that in this case, x, okay, the graph is always to the right-hand side of the asymptote. Okay, and so in this case, x is greater than 0. And that maps quite neatly to what we saw earlier over here. Now hold on. Whereas the things I've highlighted in yellow are exactly the same, the ones that I've highlighted in orange are not exactly the same, because as we know, the idea of an inverse function is that you swap x and y around. And so what we've done here is exactly that again in the algebra. Okay, if in a stock standard exponential graph, the x-cut is always 1. Okay, so let's talk that through. In a stock standard x graph, the x-cut is always 1, because we know that anything to the power of 0 is 1. We actually get that, so we know this, anything to the power of 0, a to the naught equals 1, as long as a itself does not equal naught. Okay. We can actually just make a greater than naught. Okay, let's just quickly undo that and discuss that for a moment. So we can actually put this all together. We don't have to write this two separate rulings. Okay. A is greater than naught. So we can see that here in the logarithm. If we come down here, okay, it's going to always have an x-cut of 1. Okay, and so let's think that through. That is because log any value of 1 equals naught. K has to be greater than naught. There's a second key point that we know is always true for every single exponential function. Okay, so let's just look here quickly. Okay, what would happen if I put 1 in? If I put 1 in, I would get k out, because we know that anything to the power of 1 is itself. So therefore, we should also know that a second rule that comes out of the logs is that log k of k equals 1. And those are two nice little rules to learn. Okay, they are quite useful little things to learn. Okay, they're what are called the log identities. Okay, now again, what's quite interesting here is we are now starting to refer to the log identities, again, key things that are true for all logarithms, but we're talking about identities. We know that there are exponential identities. So again, if we go back to looking at things that we know that e to the naught, not e to the naught, we know that a to the naught equals 1 if a is greater than naught. So we know that therefore log a of 1 equals naught as long as a is greater than naught. We know that a to the 1 equals a as long as a is greater than naught. So therefore log a of a equals 1 as long as a is greater than naught. Okay, now these, the CAPS document tells us, are not for manipulation. There are laws that you need to know, but they are not to be manipulated. You'll not be expected to manipulate them. In my preparation for these lessons, I cannot find a single exam example that uses these laws, but they are in the CAPS document, so I feel obliged to show them to you. Okay, so law 1 of logs of exponents was a to the p times a to the q equaled a to the p plus q. So when we multiplied, we added. Now, again, let's think that through. Okay, that means that log of p plus log of q equals log of pq. Okay, so when we multiplied, we added was the rule for exponents. Now it says when we add, we multiply is the rule for logarithms. However, when? It was only if we had the same bases. Okay, and so what I need to put in here is that the bases must be the same. Okay, so again, we had to have the same bases. Now let's go and look at law 2. Law 2 was said multiplying, so law 2 said about dividing. So a of p, a to the p divided by a to the q equaled a to the p minus q. Surprise, surprise, becomes log p minus log q equals log of p over q. Again, remembering that the key thing here was that the bases had to be the same. So it is log a. Okay. Law 3 was one that we should be familiar with from exponents again. A to the p raised further to the q equals a to the p times q. Well, that's quite interesting because it now becomes what is very often called the p-log law, which says that log base a of q raised, actually, let's just use capital letters like I did just now. Okay. Being raised further to the power of p is going to become p times log a of q. So when you had a power to a power, you multiplied. So again, when you have a power, something to the power, you multiply. Okay, so that's very often called the p-log law. Okay, many teachers or many sources refer to it as such. And the last one is actually quite interesting because it talks about what to do if you've got different ideas. So it says log of p is q is the same as log p over log q with any base that you may choose. So you can choose any base that you want here. Okay, so you can have any base that you might want over here. Okay, and so very often the context of the question might inform you, but that's more that manipulations, as we've discussed, is much more likely to occur in post-matric, as in university level discussions. You just need to be able to recognize these laws. Okay, so again, the key concepts which from today's lesson are that the exponent and the logarithm are the inverse function of one another, that the base of the exponent is the base of the log, and inversely, the base of the log just becomes the base of the exponent, that we can use the definition to solve exponential equations in the same way we can use the definition to solve logarithmic equations, that if you're familiar with the idea of an exponential graph, we can use the inverse concepts to get the graph of a logarithmic function. Okay, and again, all the things we've learned elsewhere are consistent. The x and the roles, the x and the y, have simply swapped around, and the graph is a reflection of the line y equals x. Any restrictions that we might find on an exponential function can be seen in a similar manner to be restrictions in a logarithmic function, and whatever's happening in a logarithmic function can be seen inversely in an exponential function. Okay, and then we saw that there were some logarithmic identities. Log of k is 1, and log k of 1 is 0. Okay, and then we saw that there are some log laws, However, the good news is that we probably don't need to use those log laws for any sort of manipulation in exam contexts. They just require you to know what those log laws are. Okay, logarithms and exponents have come to an end. Thank you so much for being with me today. Have a good day.